All right. So yeah. All right. So yeah. So thanks everybody for coming to Design at Large. And our speaker today is Gregory Abowd, who's coming from Georgia Tech, or coming from Georgia Tech. And a little aside, he's my academic grandfather, and so I'm excited to hear his talk and you know introduce it to everybody. So just to read his bio a little bit. So Dr. Abowd is a Regents Professor and J.Z. Liang Chair in the School of Interactive Computing at Georgia Tech, where he has been on the faculty since 1994. He also serves as an Associate Dean in the College of Computing. And applied computer scientist, Dr. Abowd's research interests concern how the advanced information technologies of mobile, wearable, and ubiquitous computing impact our everyday lives when they are seamlessly integrated into our living spaces. Dr. Abowd's work has involved applications as diverse as education, home life, and health. He and his current and former students are active inventors of new sensing interaction technologies. He has recently helped to co-create an interdisciplinary research effort, Cosmos, which investigates the collaboration of materials, manufacturing, electronics, computing, and design to explore an alternative future computing industry. So, Gregory, I'll let you take it away.
Thanks a lot, Edward. And yeah, I was very happy when I learned that Edward was going to end up at UC San Diego. And I'm sorry that I'm not able to be there in person, but I guarantee that I will find an opportunity to come visit in person. And so thanks for this opportunity to just talk about what's been a thread of research for me for the last 5 or so years. And I give it this title here, Internet of Materials, which may or may not make sense by the time we get to the end of the talk and we can discuss. So let me just tell you a little bit about what I want to do here. It's always a good practice to look at past visions of the future and try to reinterpret them in the existing context. And that's exactly what I'm going to do here, looking at Weiser's initial vision of UbiComp and kind of reinterpreting it in the context of our technological landscape of today, or more correctly, of the technological landscape in 2016 when I started doing this work. And that got me thinking about this new technological idea that I'll call computational materials. And I'll provide you some examples of this from work we've done over the past few years. There's some newer developments that I'm unfortunately haven't been able to weave into this talk the way I wanted. So I apologize for that, but I'm happy to talk afterwards about directions we've taken over the last year or so to give you a more updated version of what we're doing. But then I'm going to wrap up the talk by describing what I think are some interesting research opportunities in this space of computational materials, and then hopefully give you some parting motivational thoughts. So let's revisit Weiser's original vision. And I think for this particular audience, I think it's probably safe to say that you're familiar with Mark Weiser, but this work that I got into in computational materials happened when 2 of my colleagues, whose pictures I'll show at the end, came to me and talked about some advanced work they were doing in nanomanufacturing, being able to bulk manufacture and grow high performance transistors. And they had no idea what they might be able to do with this technology. And someone told them they should come talk to me. And the first question I asked them was, have you heard of Mark Weiser? And they looked at me blankly. And so I gave them a copy of the article. And I said, you probably only need to read the first paragraph to understand why I'm interested in what you're presenting. But I hope those of you who have read this, and those who haven't, you should, remember this very eloquent first line from the paper: the most profound technologies are those that disappear. So this is from work that started in the late 80s. This paper was written in 1991. The second sentence is the one I want to focus on. They weave themselves into the fabric of everyday life until they're indistinguishable from it. It's probably very familiar to people who've done any work in or know about mobile and ubiquitous computing. But that second sentence was written with the intent of being metaphorical. But in 2015, 2016, you could interpret this and try to understand what that might mean in a more literal sense. And in fact, back in the 90s, when this was initially introduced, some people did try to interpret this literally. For example, the people who were working in the area of smart dust at UC Berkeley, that was in the mid to late 90s, had similar ideas of technology shrinking down so small that it could literally become invisible to the human eye. And they envisioned ways of being able to produce these wireless sensor networks of these invisible devices, but they didn't quite get there with what technology could do in the late 90s and early 2000s. But it's a different landscape we have today. But if we look at how Weiser's ideas and others have influenced us, you could argue that one incarnation of that vision of ubiquitous computing is what we call today Internet of Things, or if you're more on the computing side of things, you might say it's what edge computing is about. But if I take do a Google search on Internet of Things, I get an image like this picture here. And when I look at that picture, I say, well, those aren't what I think of as things. Those objects are clearly, to me, computational. If I would do a search on things, I get pictures like this. Those objects are everyday things. These are the objects that are kind of on the edge of the world, of my physical experience, the things that I touch directly. But there's clearly a difference between these kinds of objects and these kinds of objects. Although there's an overlap, you'll see in this picture of things, there are some computational things, like there's a computer or / laptop or TV sitting here, but the vast majority of these objects are not things that you would immediately identify as being computational. So let's do a little bit of a thought experiment here and think about what it would mean to take cheap everyday things like a Post-it note and make them computational. So you're all familiar with Post-it notes. I have a stack of them that sit here. You know, easy to use, very flexible, can use for lots of things, but I don't think about a Post-it note as useful as it is. I don't think about it doing anything remotely close to computational. For example, I couldn't imagine today peeling off one of these sheets of Post-it notes, writing a message on here that says, please touch and speak your message to Gregory. And what would happen if I put that on my door and someone put their thumb on the red dot, what they would speak would then be transmitted to me. Right? That's computational, but I don't have that thing. And certainly what I like to do when I'm physically with an audience is to talk about how would you prototype something like that today? And I think you could prototype something like this, but it would probably not be very cheap. I mean, a Post-it note costs way less than a penny. So your computational prototype of what I'm showing down here probably would cost significantly more than a penny. And it probably wouldn't have the form factor or the properties of a thin piece of paper with a little bit of glue on the back that you could attach to things, right? I want that kind of form factor. I want that kind of computational capability. I want that cost. But we can also think about things today that are computational, like this form of, I think that's the Fitbit Flex 2, costs about $100, lasts about 2 weeks on a single charge, and can do simple activity recognition and quantifying. So count the number of steps and reflect how far you are toward a goal. Let's contrast that with this silicone bracelet, which when bought in bulk of maybe 500 or 1,000 at a time, you can get for a few pennies, maybe 4 or 5 cents. Any color you want, you can get it, any message you want printed on top of that, waterproof, lasts forever on no charge, but it doesn't do anything computational. What would it mean to be able to create something that I'll just call this mythical object called the infinite bit, which would have all the properties of the silicone bracelet, have it in a variety of colors, very cheap to purchase, but it could do some of the things that the Fitbit does, like it could count the number of steps, right? That would be a computational thing like the Fitbit has, but in a cheap, recognizable, everyday form factor. So those two things I showed you, that electronic Post-it note, this infinite bit, those are two things that I want to kind of aspire to. And I hope by the end of today's talk, even sooner than that, I can persuade you that these goals of producing that cheap thing with a computational capability, or making a computational thing done cheaply and in a self-sustaining way, we're not that far off from being able to do things like this if we just put our minds to it. But what does that mean? Well, why don't things, like I showed you before, why don't they compute today? And I think there are 3 reasons. And when I show them to you, I don't think you'll be all that surprised. The first is that mobile devices need an energy supply in order to do computational things. And that's a challenge. Also, though, we need to make things, be able to manufacture things at scale simply to be able to drive down the cost. And I'm not talking about driving it down the way integrated circuits and today's computing devices have driven down the cost, because they haven't really come close to the price of a Post-it note when we talk about computational devices today. But also, computational things today don't look and feel like everyday objects, as I was trying to demonstrate before. So what I want to try to stress in the work that we've been doing over the last few years is to take these three design dimensions very seriously and try as best as you can to simultaneously satisfy all three of them. And what that means is producing things where you never have to do anything explicit to provide it power. You don't have to plug it in, you don't have to change batteries, you don't have to recharge, right? So never change a battery. You want to use materials and manufacturing processes that allow you to produce at large scale so that things can be truly cheap like Post-it note cheap. And finally, you want the things that you produce, though they provide computational capabilities, you want them to look and feel like everyday materials. So these are three driving dimensions of the work I'm going to try showing you. And we haven't gotten all the way there, but that's the goal, okay? So let's take those three dimensions now and let me demonstrate you some examples of how we've tried to follow those guidelines in what we're trying to produce. So I'm going to talk about three projects that we've worked on over the past few years. I'll talk in a reasonable amount of detail about the first one, a little less detail about the second one, and even less detail about the third. But all three of these are things that have been published in the last 2 years, and you can find out more about them beyond what I say today, or certainly ask questions. So the first one I want to talk about is a project called Saturn. It has a number of other names, but Saturn is the name I'll refer to it. And this is work by one of my senior PhD students, Nivedita Aurora, who is co-advised by myself and Thad Starner, a wearable computing expert, but also in collaboration with a very famous material scientist at Georgia Tech named Z.L. Wang. And the idea here is to try to use mechanical sensing and materials that harvest energy from mechanical sensing phenomena, and add to that the ability to do passive or battery-free wireless transmission, and see what you might be able to do with that capability. So you're going to get power from vibration, and I'll specifically show you generating power from sound as the vibration using a particular phenomenon that was invented by Z.L. Wang called TENG that I'll describe. Going to use simple materials, paper, plastic, copper, and resulting in a form factor of a thin, multi-material, flexible material like you see in the image on the right-hand side in the bottom. So let me talk to you a little bit about how TENG works. TENG stands for Triboelectric Nano Generator, and it has two pieces to it. The first is a simple idea of the redistribution of charge when two materials come in contact. And a simple way you can think about that is if you were to take a plastic comb and comb through your hair, if you had hair, well, if you had more hair than me and you had longer hair than me, what you would notice is as you withdrew the comb from your hair, the hair would follow along. Why is that? Because there's a static electric attraction between the two surfaces. One of those materials acquires a positive charge when it comes in contact with the other acquires a negative charge. This triboelectric exchange of charge is something that happens between any two materials when they come in contact with each other. So that's the first part. Two materials come in contact with each other and there's a redistribution of charge. When they get separated, that redistribution of charge produces an electric field, an electric potential between the two surfaces. If you provide a path for that electric field to balance itself, that would be a balancing in a process called electrostatic induction. So now you have contact and separation creates an electric field. A rebalancing using through electrostatic induction, if you continue to contact and separate, you essentially produce an alternating current. The image in the upper right-hand corner is showing you that simple animation is showing a continuous alternating current that's being produced by redistribution of charge and electrostatic induction balancing of charge. Now, what's showing up in the middle here? In the middle, what's labeled with Saturn is the multi-layer material that is designed in such a way to maximize the amount of vibration that an incoming vibrating source provides on that particular surface. I'll describe a little bit in the next slide what goes into that multi-layer material. But the sound is a vibrating source. It causes that Saturn multi-layer material to vibrate, which produces an alternating current. And furthermore, that alternating current, its amplitude, is directly affected by the amplitude of the incoming sound. So now the alternating current is essentially a copy of the audio that was incident upon this material. And it took no additional charge or energy to do this. This is a sensor that's using the phenomenon that it's sensing to power the sensor itself, a kind of self-sustaining sensor. So let me show you a quick little video. It's not quick, it's about a minute long, that shows the different layers. There's no sound here. And Edward, just make sure, let me know if people can see the video here. Thumbs up? Yeah. Okay, so I'll start it over because I want you to see these first things. There's a couple of layers here. So this is a layer of plastic with copper deposed on it. And then you've got a piece of paper. And the paper, let me go back real quick to show you that paper. So this paper has copper deposited on its other side, but you'll see here, you can kind of see through that paper. There have been a bunch of laser etched holes in that paper. And the reason that's done is because that will help when the two layers are put together, that will maximize the amount of micro vibration that occurs between these different layers. So I'll continue the video here. So there's essentially 4 layers, 2 copper, 1 paper, and 1 plastic. Now to put these pieces together, we're going to create the electrodes that connect copper from one side to copper of the other layer. So that's what's happening here. Things are being placed against it. And all this is doing is creating a electrostatic induction path for the 2 layers of copper. And then what's going to happen is the paper with its copper is going to be attached to the plastic and its copper. And that's going to be done with 9 glue dots. And then these things are attached. And voila, you have your handmade Saturn patch. So it's a fairly simple manufacturing process. This is just a mounting frame that's put on here for experimenting to collect data from it. Okay, so but that's just a sensor. All that can do is, without any additional power, it can produce out of its electrodes a signal that reflects the incident voice sound to it. And now we're going to use a trick that we also didn't invent. We didn't invent TENG, although we perfected it in this particular form. And we didn't invent this form of passive or zero power wireless communication called RF backscatter. So this is fairly well known over the last 5 to 10 years in a number of electrical engineering and some ubicomp domains, a way of being able to use the fact that an antenna will reflect an incoming radio signal. And if you tweak the parameters of that antenna, you can essentially tweak the backscattered signal. So the tweaking that's happening here is essentially a modulation of the antenna based on the sound that is incident upon the Saturn patch. So what gets backscattered, the amplitude modulation, is going to encode the audio signal that was incident upon the patch. So you have an ability to do a battery-free wireless audio material. And I'll just show you a quick, and so this is what it looks like today. And that's what I was proposing we might be able to produce. So this is a paper-like material. You can write on top of this. It's not as cheap as a Post-it note now. And as of 2 years ago, here's how well it works.
We present our work Zeus, the zero-energy ubiquitous sound sensing surface. Our setup consists of an RF transmitter, receiver, and Zeus patch placed at a distance. The transmitter broadcasts a carrier wave at 915 megahertz, which is received and amplitude modulated by the Zeus patch in the presence of slight vibrations, like speech or touch. The modulated signal is backscattered to the receiver. and the audio information captured by the patch is extracted. Let's look at an example.
Hello, hello. Audio from Zeus.
Hello, hello. Audio from Zeus.
So that fairly crappy signal was to the raw audio that was wirelessly transmitted back. We could do much better today, both in terms of the form factor of the antenna. It was a pretty clunky printed antenna on that past example. And we can also further process the audio signal to clean it up as well, but get a better transmission as well. So that's what we could do. So that's one example of a computational material. So that's a material that can transmit wirelessly any kind of mechanical vibration like sound. So the next example I want to talk to you about is how you can use a pretty low power mode of sensing, in this case, what's the equivalent of a photodiode, and use that to determine activity around the photodiode. And in this particular example, this is work of my student Dingtian Zhang and a colleague who's going to be defending his PhD thesis tomorrow, Yang Zhang, who's at CMU, with people in electrical engineering who are experts in optoelectronics and printed organic materials. So Canek Fuentes and Bernard Kiplin. So in this particular example, we have three different arrangements of silicon photodiodes. On the left, under the column 0D, you see that image there. There's a rectangular patch on the right-hand side. That's basically commodity, thin, flexible solar material. So that's the harvester, using ambient light to power what's going on. Right beneath it is a PCB, that is the computing and wireless communication capability. You can see it exposed in the other two examples more clearly. But on the far left edge of that, there's a single black dot. That's just a single photodiode. So this doesn't need any replacement of batteries to do it, but it's a pretty large form factor. But what can you do with something that's just a single photodiode? Put that on the edge of a door, and as you open and close the door, revealing and turning off the light tells you about the door being opened or closed. Put it on the inside of a bottle, and the opening and closing of that bottle reveals a different light pattern, tells you whether the cap has been taken off or placed on to the bottle. Put those silicon photodiodes in a 1D array, and you can do a variety of things, like line it on the inside of a container, and you can measure how high liquid container goes in there. You can use the property of the liquids to do a classification of what kind of liquid goes in there. But I'm going to show you in the next slide something that you might be able to do if you place something like that around your wrist. On the right-hand side, we see a two-dimensional array of these things. You can essentially produce here a battery-free, hovering, multi-touch surface. So let me go back to this one-dimensional array of these. And here is an example of Dingtian walking with the 1D array around his wrist. As he walks, you'll see in the graphic on the left, sorry for the music, he's actually counting his steps as he walks. So that was an example of the infinite bit in action, not quite the same form factor as the silicone wristband I'm showing you here, but it doesn't require a battery, and it can reliably count the number of steps. Now, this was all done with traditional silicon-based photodiodes. But I said the colleagues we're working with are in printed organic electronics. So in the middle here, you see an example of photodiodes that are printed on a thin film, so they become flexible. And so this was an early prototype of the two-dimensional optosense that would do the be able to detect hover and steps. We've made lots of progress on this, particularly in the last 6 months that I'm dying to show you, but I don't have it quite ready to show yet. But I'm very confident that we're going to be able to produce something like the infinite bit in a form factor that's much like the infinite bit. I don't think it'll be 4 cents, but I think it'll be closer to $1 than it'll be to $10. So we're able to produce something that's a self-sustaining activity tracker. The last one I just want to briefly talk about, this was also presented at the last UbiComp conference. This is an entirely different approach to being able to produce a surface that is paper-like, but that can detect gestures on the surface and wirelessly transmitted. So it's similar in spirit to the OptoSense 2D hover multi-touch surface that I talked to you about, but it's done a different way. This is done with very cheaply printed crisscrossing conductive lines, simple computation to create an XY pattern, and then using frequency shifting and an FM, as in FM radio, form of backscatter to be able to communicate this to an FM receiver that's in your pocket, that is your smartphone. So I can go into more detail about this, but another example of low power enough that it can be sustained with ambient lighting to provide its power and do a wireless transmission. So those are three examples at varying levels being driven by the power, scale, and form factor arguments. Now I want to step back from that idea of those computation materials to talk a little bit about what are some of the research challenges in this area. So I think there are at least 4 different categories that we can think about, and I've highlighted the 4 here. The ones I've underlined are the ones I'm going to talk a little bit more about in the subsequent slides, but I'm going to just quickly go over points 1 and points 3, and we can talk about those more. In fact, point 3 I'll come back to at the end of the talk. So let's talk about number 1 here, power savvy platforms. What I want you to do after this talk, or you can do it right now in the talk if you want, is go to Google or Google Scholar and look up battery free. And you'll see that over the last 4 or 5 years, there have been a variety of interesting papers that have been presented that are battery-free examples of what's starting to approximate consumer electronics. This is an interesting emerging field. How do you produce things that can sustain themselves by harvesting energy either from the way they're manipulated or being so low power that they can use traditional commercial or commodity harvesting techniques, whether it's heat or light or vibration, to be able to produce enough power to do something interesting. The other piece that's going on in power savvy platforms is the ability to make it easier for hobbyists and inventors to do the same thing on their own. So the harvesting equivalent of having Arduino platforms that make it easy for people to teach themselves how to do their own kind of electronics. So democratizing harvesting solutions and providing them in enough variety and simple enough to use that people can start to build their own self-sustaining solutions. So these are very interesting trends in the power savvy platforms research area. In production practices, I'll come to this at the end, but the moral of the story is that we have been too constrained in the computing industry of thinking about the one true way of manufacturing cheap computation. I think there's at least one other way we can think about that, and I'll return to this at the end. So I'm going to focus on here are prototyping user experiences and principles that we can use to either motivate, drive, or check, put limits on the kind of innovation we want to do with these computational materials I've showed you. So let's go back to these aspirational goals that I showed you. I talked about an electronic post-it note. There's the incarnation of that electronic post-it note that does a wireless transmission of audio. I talked about being able to produce an infinite bit, and I hope I showed you that both of these things are not that far off. It's possible to produce self-sustaining, relatively inexpensive, flexible, conformable, interesting form factor versions that do these things. So I hope you're convinced that these things are not that far off, but you might not care, right? And I think it's very important to say, well, yes, we can do this, but so what? Why should we bother? Let me try to address a little bit about that. So let's take the example of the Saturn patch that is the a distributed microphone. And there are at least 2 scenarios in which this would become useful. So imagine you're in a crowded auditorium and speaker has ended with their talk and you want to ask a question. You're sitting in the middle. You can either shout, and that's sometimes not polite, also sometimes not useful for people who are using assistive devices to understand what's going on. So you need to approach a microphone. So you can either have a wireless microphone passed to you, or you can crawl over everyone and get to the aisle and queue up at the microphone. But what if everyone in the audience had a piece of paper like this, that when they put their thumb a particular way and they simply spoke into the paper, it would amplify what they say so that everyone could hear. And if this was cheap enough, this could be on your badge at a conference and be a marginal add-on cost. Another example on the right here is you're in a conference room and you're having a remote conversation. Rather than having microphones that are embedded into the table or something you have to pass around, again, you can have a set of these pieces of paper. Maybe they look more like a coaster. You can pick one up, you can hold it in a particular way to activate it, and then you can speak into it. So we can have self-sustainable distributed microphones. Okay, but you still might not care. And I wouldn't blame you. But let's think about health. So in my field, in the field that Edward's in, and he's actually done a lot in this particular area, we look at leveraging commodity platforms, specifically the smartphone, to sense things that are of interest from a health perspective. So there are plenty of examples of using these commodity devices to generate and sense clinically relevant information for asthma, stress, jaundice, social engagement. The list goes on and on. But what you don't see is that our everyday surfaces being empowered with this capability. The walls around us, the tables, our clothes, the tissue that we might use. And the question is, why don't they do that? And I would argue because it's too costly now to do that. People have already invested in this multi-$100 platform they have in their pocket, so let's take advantage of that. But there are some limitations, I think, to that approach. And if we could make the surfaces around us cheaply enough to have these computational capabilities, it might open up opportunities for trying to explore how we might turn those surfaces into meaningful sensors. So let's take a relevant kind of object from today, an N95 mask, and say, what would happen if we added the Saturn harvesting capability to this so that the mere breath coming from your mouth would be enough to power this, to enable it to measure your temperature and then transmit that to some nearby device, or to count the number of breaths, or to record the quality of your breathing and communicate that somewhere else. There's a variety of those kinds of meaningful applications we could have, but it only really makes sense if we can do this in a way where it's cheap enough that these devices can be ultimately disposed of. And we're not quite there yet, but this is something that I think we could aspire to. Or you could think of other kinds of surfaces where it might make even more sense to be able to do interesting health kinds of sensing. And I think these opportunities are available to us now. You can also think of other uses for vibration or ultimately mechanical sensing. So here's an array of the Saturn patches. So what might you be able to do with large scale surfaces? Well, you might be able to create an even more sensitive audio sensor or a more powerful one that harvests more energy. You could put something like this on heavy machinery, like an aircraft engine, and you could monitor the vibration and determine interesting or worrying patterns of a shift in that vibrational pattern. You could put things like this on surfaces and you could walk over them. You wouldn't identify who's walking over them, but you could measure that someone is walking across a particular surface, and you could embed it permanently in carpeting, tiles, or sidewalks. If we were able to increase the resolution, we could turn the act of writing, which is ultimately sliding a mechanical vibration across the surface, as producing enough energy to record actually what's being written by ordinary objects like a pen or a pencil on that particular surface. There are lots of ideas that you might pursue with something like this. From the perspective of an industrial designer or a designer, that's not what really excites them. So I have a colleague here, Hyunju Oh, who's a professor in industrial design at Georgia Tech. And she saw things like the Saturn patch, and what interested her about it was that it was like the physical materials that designers use. So it can be flexible, can be embedded onto things. And the fact that it had computational capability was an added plus because it allowed them to be even more creative. So they took the Saturn patch and they turned it into the ears of this elephant. And so you could whisper to the ears of the elephant in that three-dimensional shape. There are lots of much more creative things that designers would do with these kinds of computational materials than I'm able to imagine. So we empower a whole new level of creativity when we take advantage of the materiality of the computational device we're producing. Next point about principles. What things do we want to use to motivate or to put some sort of control or checks on what you might want to do with computational material? I'm not sure about this, but I'm reasonably confident that at least one of you in the audience saw the work of the Saturn patch and being able to create a material I could place anywhere that could wirelessly transmit audio, and you were a little freaked out about that. And you'd say to yourself, well, that's not a world I would want to create. And I respect that. And I think that's the right kind of skeptical, hopefully constructive criticism you might have of this particular work. But beyond issues of privacy and security, there are lots of other principles that we might want to support. So how do you make things that are biodegradable or non-toxic, or they're made from renewable sources, or they're not biased toward one class of individuals over another? And my comment to that is to look at the stack that we're talking about here. And in the past, as people who build applications with existing computing, we were given the computational device. And so any property that was impacted by the way that device was constructed, we had no control over. So if I want to make a biodegradable computer today, I would have a really hard time going to Adafruit or whatever and buying biodegradable integrated circuits. Right? So if I really care about biodegradability, I have to have control over the materials that are used and the way they're put together. And if I don't have that control, some of these properties I don't have a chance of being able to address. So breaking that divide will allow us to think about where can we design in the properties that we care about, and when in this stack is it too late. I think from the perspective of privacy and security, it's not too late after things are fabricated to respect privacy and security, but there might be things about the physicality of something that make it easier to ensure privacy or security with the materials that we produce. Certainly from the perspective of biodegradable, non-toxic, made from renewable resources, I would argue if I can't get at the materials, I probably don't have much of a prayer of being able to affect those properties. So now I'm just going to close with a few general thoughts, hoping to motivate you to want to think more seriously about this area of computational materials. So what I motivated this by was reinterpreting Weiser's original vision of what does it mean to weave technologies into the fabric of everyday life until they're indistinguishable from it. So the technology that I'm proposing is computational materials. And this is what I consider to be the material for the 21st century. Weiser's book article was about the computer for the 21st century. So a quick spin on that, saying we should be able to build computational objects that are functional materials, that are self-sustainable with respect to power, and they can perform any or all of the things that we expect a computational device to do. And in addition, they can be manufactured in large quantities at low cost and look and feel like everyday objects. If you're interested, you could read this top article that I published in 2016 that was talking about a progression of 4 generations of computing technologies, the third of which was Ubicom, Weiser's vision. And then the fourth I proposed emerged in the 2000s. Here I'm proposing, from 2020 onward, we have a 5th generation motivated by computational materials. And I've written about this in a recently published paper entitled The Internet of Materials, saying we shouldn't be thinking about the Internet of Things. We should be, or we should interpret things more literally. So can't say Internet of Things because that already means something today. So I coined the term Internet of Materials for what I view as the opportunity for these computational materials. But what I talked about a little earlier is that we have to rethink how we produce or manufacture computational entities. And what I mean by that is we have to be less constrained by the current prevailing mode of how we manufacture a computing device. So Moore's law, which has been in effect, arguably still is, maybe not, that doesn't really matter to me, but since the mid-60s. And the idea behind Moore's law is that colloquially, we think of it as computers always getting smaller, cheaper, and more powerful. And the reason that that has been so wonderful is that we can see many examples in the technological landscape over the last 40, 50, 60 years that show that in laptop computing, in mobile communications, in augmented reality, virtual reality, examples of those technologies in their beginning on the left side in each of these diagrams, wait 30 years, and Moore's law automatically allows you to have things being cheaper, better form factor, more powerful, and more appealing for that particular domain. And there wasn't really much that researchers did in those domains of mobile communications or AR and VR. Moore's law basically solved the problem for them, made platforms better to do the examples that they wanted. So this is why Moore's law is very compelling, because we've seen that it solves a lot of our problems. If we show a clunky prototype and it's not running in real time and it's a little bigger and more costly than we want, then the reaction is give it a few years. Moore's law will solve those problems. So that's why we love it. So that's Moore's law thinking. Computers will always get smaller, always get cheaper, always get more powerful. Now, many people don't think that that's true anymore and provide compelling arguments as to why that's not true. But true or not, I think it limits our way of being creative with computing. And so the vision that I have is that if we think in terms of these self-sustaining computational materials, and we think that I showed you really crufty examples from the late 2010s, but what will computational materials be like in 2025, 2030, 2035, 2040, if we have them constantly getting more large scale, cheaper, and more functional? They'll go from this simple example of the early Saturn patch and the early OptoSense infinite bit to materials that look more like our everyday objects and are cheap and do increasingly sophisticated things. And that's a different, and it's only going to happen if we rethink the way we manufacture. We break out of the key to Moore's law, which was integrated manufacturing, to more different ways of thinking about manufacturing that chemical engineers have always thought about in terms of modularized bulk manufacturing techniques. And that little image, the rod in the middle there that has the gold dot on top of it, that's an example of a grown NPN transistor that my colleagues are able to grow in the billions in a lab at Georgia Tech. But now, what do you do with those? How do you use additive manufacturing techniques to take those high performance devices and turn them into interesting computational materials? So of course, to do this requires way more interdisciplinary perspectives than I have myself as a computer scientist and human computer interaction or applied computing one. It involves expertise from material science, chemical engineering, mechanical engineering, electrical engineering, computer architecture, industrial design, ethics, policy. So if you're interested in this kind of work, my message to the students or people looking to go in a different direction is you're gonna have to either educate yourself in these other fields or start to align yourself with people who have this expertise and get them thinking along the lines of what computational materials might do for us in the coming decades. And of course, the people who really do the work are the students who have taken this to heart and have themselves trained themselves to have these different disciplines. And I acknowledge a number of those on this particular slide. And with that, I will stop and I'll take any questions or engage in any kind of discussion that you're interested in. Thank you very much for your attention.
Do you want to stop sharing so that everyone can see your face?
Sure. Although I may end up coming to some of these slides. But
Okay, then we'll just keep it on there.
Well, I stopped already. So.
Awesome.
Someone wants to ask a question over the mic. Of course you can.
Hi there, let me thanks, that was a really interesting talk. So one thing I was wondering about the whole time was, would you say going forward as we have like all these new ways of interfacing with computers and the internet, they'll just start to add on top of what we have right now with like smartphones, since we already have like a very useful tool for that, but it's also like very obtrusive in our lives. Might we be able to offload some of those things that we use our smartphones for and allow us to still like utilize the internet to better ourselves, but not have this source of consuming content constantly distracting us?
Yeah, so Jackson, right? Yeah, so 2 points there. One, I think every generation of technology, I was presenting computation materials as the 5th generation. I think every generation relies on and builds on top of past generations. So we've not gotten rid of mainframes. We call them the cloud now, but we haven't gotten rid of high performance computing. We haven't gotten rid of desktop or personal computers, our laptops. We won't get rid of smartphones. But your second point, about how you offload your attention. I think that was a lot of what Weiser was trying to get at when he talked about profound technologies disappearing. In the late 80s, that was the world of desktop computing. And he wanted to remove our attention from sitting in front of a desktop. And I think smartphones have allowed us to do that. We now stare at something while we're walking or while we're sitting on a bus. But you look at a lot of the marketing for smartwatches, and a lot of what they were trying to say was this smartwatch is going to offload the need to have to take all that effort to dig into my pocket and pull out this device and turn on its screen and go to the right application. I can get it, with a flip of the wrist. A lot of what motivated Google Glass was being able to essentially make certain pieces of information immediately available to you. So I do think there is a desire to, smart speakers in your home allow you to ask verbally questions so you don't have to pull out your phone and search for things. So there is a lot of motivation for allowing us to direct our attention to other objects in our environment that are also internet enabled to be able to do computational things. And the question is, well, will computational materials help us in that direction or not make a dent in that direction? I think what I've shown you is mostly just sensing and communicating devices. And I think there's a limited opportunity for those to allow us to offload things. So I can take one of these Post-it notes and I could place it in my closet, and it can essentially be an extension of my Echo or Google Home or Apple, whatever, so I don't have to buy another one of those devices and place it nearby. So that allows me throughout my environment to be able to provide audio input, but without having some kind of actuation, some output or movement. I think there's limited opportunities. So I'm pushing a lot on trying to do output these days. Thanks for the question.
I'm curious about the output part. Could you expand a little more on that?
Sure. And there plenty of people have done much more on the output side, although I don't know that they take as serious as I would want them to the self-sustaining aspect of it, but the area of metamaterials. So being able to use either electrically or heat activated or chemical activation to allow some composition of materials to change its shape or exhibit some kind of behavior in changing conditions. But also there are an emerging class of extremely low power inks that can be activated by small electrical energy, electrochromic inks in particular. So I think we have the ability to think, to dream in a way that's not too fanciful, that we'll be able to produce reasonably high resolution painted surfaces that are addressable and electrically activated and do not require a lot of energy, at least to produce semi-bistable, by which I mean a little input of energy can flip its state, and that will persist for 60 to 90 seconds at a minimum. And that, I think that's going to get better. So I think we're nearing a time when we'll be able to put on our multi-layer conformable, thin, flexible things, the equivalent of a display, a low res display to start, but Abowd's law, in 5 years, it'll be, twice the resolution, half the price, and more functional and more color.
So
Greg,
I said, don't be shy, go.
Okay. Yeah. So Greg, I actually have a lot of questions. First off, it was an amazing talk. There's like a lot of points there. It also made me think a little bit about Project Jacquard from Google folks. Yep. And one of the things that this computational materials inspire on me is the fact that today, if you think about people making computational devices, they have to have some knowledge of computer science or circuits, and they have to put things together. And the argument they were trying to do in Project Jacquard was, well, now you can literally weave a piece of technology into something that you are making, and you don't need to learn computing to use the technology. And I see that your work has something along those lines where I don't really know how those sensors work, but I can make one in my spare time. It's very cheap to make them, and cheap in the sense means I can make it without a lot of effort. And I now have a sensor that can hear, or a sensor that can detect light changes. So you
Yeah.
you hinted a little bit when you were talking about the designer using it, but maybe you can expand on the
So
direction.
again, I have two reactions to that. One is from a research perspective, to make these kinds of breakthroughs, I think that the people who are going to demonstrate these, so my students, for example, they have had to teach themselves skills that they didn't get as software engineers or computer science undergraduates. The age of UbiComp taught us that to be a successful and impactful UbiComp researcher, you needed to be comfortable with electronics as well as software. The age of computation materials is going to tell us that in addition to that, you're going to need to be comfortable with materials. But that's from a research perspective. I think there's a wonderful opportunity as researchers to start to democratize all of these things and produce solutions where end users aren't going to have to understand why that triboelectric effect works and why those particular materials were chosen. They will just know that I can either buy that off the shelf or I can put that together myself. So we both have to, push the ceiling, and to do that, you're going to need to have people, teams of people or individuals who have these additional disciplinary skills, and also raise the floor so that not everyone has to have those particular skills. And those are two different and important research contributions we have to make.
I have a question. So this is all fascinating, but I'm thinking about the future of teaching students. I'm part of a the future of undergraduate STEM planning committee meeting, and when you're talking about this demand for this interdisciplinary mode of thinking, I'm excited. But by the same token, we are in no way, shape, or form prepared in a systems sense to have the next generation do that. How are you thinking about these are going to change the way we actually educate people to be content creators or technology creators?
Yeah, well, so a couple of ways. Number one, we've started to teach interdisciplinary courses that add materials and manufacturing and computing and design to initially undergraduates and graduates. I did a 5-week course. The day it ended was the day Georgia Tech's campus closed down, March 13th. And we just took people from these different disciplines, put them in the same room. And a lot of what goes on in this initial education is just understanding the vocabulary of different disciplines and what drives them. So having just simple introductory lectures from people in these fields to say, here's how we think as a material scientist. Here's how we think as a chemical engineer. Here's how we think as a radio communication electrical engineering specialist. Here's how we think as an industrial designer. And then give them projects to work on that bring these things together. And ultimately, how do you really drive that in? You do it earlier and earlier in the educational career, and get people to understand that, we live in a world that far too much values specialization, and that limits kind of, invention in some ways. So you have two approaches to that. You either educate yourself to get lots of different skills, or you educate yourself well enough that that to do something interesting, you're going to have to work with someone else who's an expert in a different field. And that's a lifelong lesson for people to listen, because in 20 years, when computation materials is just assumed, and I'm a trillionaire beyond belief because of my visionary ideas, there's going to be something completely new that we'll have to think about.
One more question from the crowd.
Thank you so much for your wonderful talk. It was really, really interesting. My name is Adriana Arce. I'm a nurse scientist at Columbia University, and I just wanted to comment that I can see so many healthcare applications for sensors that are really democratize access to these kinds of functionalities. And particularly I work in health disparities, and one of the issues that I work on is Alzheimer's disease. And you have a point where people get where they start wandering, and being able to have sensors cheaply installed in a variety of places you can keep track of a loved one who, maybe doesn't know what's going on. So really excited to see where this goes in the future. Thank you.
I love that, Adriana. And if you haven't heard of it before, you should take a look into the movement called frugal science or frugal engineering. It is driven by the cost factor. Make technologies that are so cheap to manufacture that they can be made widely available. We have, I think it's out of Stanford is where a number of the originators of this idea, and one of their descendants is now a new faculty member at Georgia Tech who I've recently met, and I heard him talk and saw some of his examples, and I said, well, that's a similar motivation. Push yourself on the extreme of the dimensions that matter, and cost matters, power matters. You may argue that form factor doesn't matter that much, but it matters to me in terms of things becoming more invisible in the sense that Weiser talked about, and seek to satisfy those dimensions in the extreme and see what you can do, and use important domains like health to justify why you do it. I think, well, we're right on the hour, so I think we're ending right on time, Edward.
Unless there's any more questions.
I mean, I have a bunch of questions.
I have a quick one if you guys will allow.
I'm fine.
Do it.
You're just sitting between me and dinner. There's no rush.
So I have a quick one. Do you guys ever either use Nike as a model? Because I know that they're making textiles that are computational, as far as making clothing that adjust to athletes and whatnot. And do you guys ever either?
Yes, I use them as a
or
model, or Under Armour, or any of those kinds of textiles. I also use companies like Corning as models, but I'd rather use them as collaborators, because what I really think is happening is that there will be an alternate computing industry that will emerge. And I don't think it's going to be the Intels or the ARMs of the world that are going to do it, because they're too invested in their current way of producing computational devices. It'll either be companies like Nike that see the opportunity, or Corning, places that already manufacture durable goods in a different way, or it'll be some upstart, the Infinite Bit of the world that shows the example of a small number of compelling applications that drives people in that particular direction. So yes, I'm inspired by them. They're the model, but I would much rather be their close collaborator. Okay, there were a couple of, so Danilo said he had some, but I think someone else also said they had a question.
I can go very quickly then. So it's very quick. It's thinking back to the idea of like invisible technology as a metaphor. And it's a beautiful way of thinking about technology, because if you think about today, when you drive a car, you're not thinking about levers or gears. The technology is invisible to you. You're thinking about where you're going. And that's very similar to what we managed to implement in computer science with computers, where I'm using an iPad with like an Apple Pencil. I'm not thinking about the technology, how it's pairing to my iPad. I'm actually thinking about the notes I'm taking and how I can easily just open those notes on my computer due to the cloud. So the technology, gets into the background. Unfortunately, for this to happen, it wasn't only a technological question of whether or not we can do it. It was also getting a company together, or people putting this technology together so it could work seamlessly. And it works really well in the iPad ecosystem or Apple ecosystem. If I try to integrate with some other ecosystem, another company, that won't work, it would break down. The Internet of Things, it's a beautiful idea, but it really breaks down because there's so many, there's so many implementations and protocols that if you really want something to work, you have to choose a single company. So I wonder if now at the beginning of maybe this new era of computing, if you're also thinking of ways of changing the way people can design this technology so things are maybe more naturally integrated, or what are your thoughts on it?
Yeah, I'm going to share my screen again here. This article I wrote in 2012, you guys see the screen? It says, "What next, UbiComp?" Some of the points I was trying to make in that article were about some of the points you were raising in terms of what remains a challenge in the third generation of ubiquitous computing. And a lot of it is that it's still too hard to program ubiquitous computing experiences. And a lot of it has to do with the point you raised about how we have to, integration is the hardest part of software engineering. You know, bringing things that are built separately and bringing them together to work seamlessly. So that's why, you know, iOS and Mac OS work relatively well together, but not too well with Windows. And you know, this is a problem that we have. And it's interesting because it's, to some extent, it's not a technical challenge. It's a challenge of standards and a challenge of a free market system that does not incentivize that kind of integrative experience. So I completely agree with you that we're still quite a long way from a proliferation of devices not complicating our lives, because the more devices you have today, the harder it is to get all of them to work together. I remember hearing a talk many years ago from Bill Buxton, where he argued that the way you should be able to sell someone on getting a smartphone is that the smartphone, when brought into their house, makes everything else work better. Not just that the smartphone itself does a lot of cool things, but it makes, you know, the things in your car work better because of its existence. And we just don't have that mindset about making things improve the overall state. I think I went off track there though, Danilo. What else were you talking about? There's one other thing. I loved your point about the iPad. Have you seen, it's probably about a year and a half old now, the Apple ad where they have this young girl, probably 13 or so, and she's going around her everyday life doing things with her iPad, and her neighbor peers over the fence and says, "Oh, what are you doing with your computer there?" And she responds, "What's a computer?" It's exactly your point about, you know, if we do these things right, then we don't think of them as computational devices.
It's an interesting point about compatibility, I think. I was just kind of imagining, what if my cup is computational and then and it's incompatible with my water heater and I can't get water? How annoying would that be?
Yeah, exactly. Right.
And those are problems we face today with technology because of the many implementations or many companies where you spend so much time just thinking, okay, I need this app to have my lights turn on at 5 p.m. But then it won't work because of a trial service. And at the end of the day, you just want your lights to turn on automatically at the end of the day. Or in healthcare, it's even more complicated because it's not even about showing the value. Sometimes it's actually, you know, convincing the cost payers that they're going to save money. And it breaks down the entire technological stack that could change things, right?
Right. Yeah, I have a lot to say on this. That 2016 article argued that if you look at each generation, it's not just the introduction of a new canonical technology, it was the adoption that was driven by some initial compelling use. And then when enough people had invested in that, the necessary infrastructure for the initial use, then you had lots of people building off of that, follow-on applications. So that has to happen. For computational materials to take off, there has to be some set of initial motivating applications, whether it's in health or in environmental safety, don't know. But that has to happen for things to be, people to invest in what's needed to make these things widespread.
Cool. Gregory, are you still free to do any of the virtual meetings after?
Yes. I think let me stop sharing my screen. I can take a look at what time I was supposed to meet with.
It's okay. It's just a bunch of my students, and I think Chris has a question, maybe a closing, brilliant question.
Yeah. So probably not brilliant, but possibly a closing question. So, you know, I think that there's, speaking just particularly in the healthcare context, because that's where it's most sensitive, you know, I think it seems like we run into a lot of instances where people build technology and the issues of privacy and security are really not thought about as the sort of technology is coming into fruition, as it's being built, as it's being constructed, and as it's being deployed. And so if we use the example for example, you know, Alzheimer's disease and the patient wandering, right? If all of a sudden I'm surrounded by computational materials that are tracking where people are going and what they are doing, and I haven't thought about in the construction of these networks of materials and in the construction of how I harvest information from them, how to build privacy and security into them. How do you think about the responsibility of, people like yourself who are thought leaders in the field of sort of computing materials and people who are constructing them? It's very, very cool to have these things and to build these things, but how do you prevent or sort of modify the trajectory of the way that we start to use these things, if indeed the trajectory of these things is to become more ubiquitous and to become, sort of more deployed and sort of more omnipresent in all of our lives, to sort of take into account the privacy and security aspects of it, because it hasn't been done in the past with all of the technologies that we sort of are, use in our lives, and we're seeing sort of the ramifications of that. And so how do you think about altering that going forward?
I was waiting for someone to ask this question, because I think this is an obvious question to ask any kind of technological advance. And it was what I was trying to hint at when I was saying, what are the principles that will either check, stifle or stop us from doing these things, or motivate us to go further. So my response to you is easy to say and hard to do. The easy thing to say is that we have to stop, as technology inventors, allowing the properties of our technologies to emerge as opposed to be designed. So a lot of the problems you're talking about with health technologies or surveillance technologies is that the problems are emergent problems. There are things that happen, good or bad, that were not thought of and were not designed for. They just emerged because people figured out really good or nefarious ways to use the particular technology. So you have to be thinking up front about, well, what are the privacy or security, or pick your favorite principle, what is my technology making easier with respect to those, and which ones is it making harder? And do I want things to be easier or harder? So with respect to privacy, we think a lot about that with respect to the materiality and the audio sensing. And that's why, and some advantage of physical objects is that sometimes we understand how they work better than computational objects. So, I can tear something up, and does that destroy something or not? When I touch something, how do I let someone know that the touching of that object is what activates it to work? The fact that something is a near field capability. So you saw in that video, Nivedita was actually fairly close to the microphone, right? So you could either say, oh, it's not a very good microphone, or, oh, that's really good. I have to be pretty close to this for it to actually work, right? But the more difficult piece of this is, what do people understand and trust about the thing that you put here? So I could say, I could produce a piece of paper that is an audio recording device, and that when the material in the corner here turns red, it's actually activated, and it's not recording if it's not red. But would you believe me? Even if that were true, would you believe me that that's true? Do you believe that the camera on your laptop, when the LED is not on, can't possibly be recording?
Definitely
no,
not.
you don't. You don't believe that. But there are ways to use physical blocking and understandable physical objects to essentially give people trust and control over these things. So we've done a project recently where it's used as computational material to essentially become a smart webcam cover. And the idea there is that it's not part of the technology, right? It's something you add on top of it. So the extent to which you trust that this thing blocks because it is a physical light barrier, then you trust that it would block the light going into the camera, regardless of what's going on with the camera and its laptop. So you have to be thinking about the properties of physicality, people's understanding, belief, and trust in these things. But the short answer is, you can't just leave the properties to emerge for the people who use the technologies that you invent. We have a responsibility.
Thanks.
JDS, do you want to? You're muted.
Is that Jessica?
Yeah.
Okay.
Yeah.
My question is kind of related to him, but it's on the side that, remember when you talked about the disposable masks and they could sense a lot of other things? I was thinking about what are we doing with all of this waste, because we have a problem right now that it is not solved yet. That is the waste, like of all the electronic materials and other things. And how do we know that we are going to build something that is not going to make the problem worse? Because we might think about using materials that are environmentally correct, but once this goes to a large scale, other companies may not think about that. And how do we act like cautious enough as designers and as creators to build something that would not aggravate other problems?
That's a great question and a great point. So I'll just quickly share the screen again. Say that was the point I was trying to get across here, where I was saying that some of these properties. So, for example, you were talking about, to one extent, are things biodegradable? When I dispose of them, what happens with the materials that I use? Now, the example of the Saturn patch that I showed you is a bad example there because it's got copper, paper, which is not so bad, but plastic, which might be bad. So how do I pick materials that would be more biodegradable, but also exhibit the appropriate triboelectric properties so that I can use it as a sensor, like in your in the PPE, the N95 example, so that it can be disposed of and you don't have to worry about what kind of waste you're producing. I think it's only when we break this barrier between device and fabrication and we have control of the constituent materials and the way they're put together that we have a prayer of being able to address things like it being responsibly disposable.
Have you had any luck in that space of finding such materials for, say, for example, for the Saturn project?
I would say no. Reluctantly, I'll say no to that. But that's more because I haven't engaged the right set of material scientists with this. And it's a different way of thinking because a lot of these people think about, I mean, there's a flip side. I can think about building things that are durable, and so they'll last for 50 years, right? We certainly don't think about computational devices today lasting for 50 years, right? But if I could produce a computational material that was upgradable, meaning its function could be improved over time, but could last for 50 years in building material, that's another way to address, well, I won't have to tear that building down in 10 years because there's a new version of computational building materials that I'd want to use. So you can both think about how do you produce things that can be disposed quickly, like the Post-it note, but made of materials that I'm not so worried about disposing of, or things that will last way longer than we anticipate. So,
but how do we get things to the point where they're like as canonical as like concrete, right? Like, these things where it's like, what's the point in upgrading it? Or, well, can't really upgrade that because that costs too much to build in the first place. Can't just go knocking it down.
So you want to hear a dream, Edward? So let's imagine we can manufacture concrete using within that concrete those high performance transistors I showed you before. And so now a building that is to house a data center actually uses the building materials itself as part of the data center. So building materials as computers.
It's a big computer.
Maybe it might not be the most efficient computer given the size, but it might be this trade-off that making it part of its structure itself allows that building to be dual purpose. It's both a data center and an actual apartment.
And I think that they're like visionaries like Asimov, that even though at his time he was seeing this like miniaturization of technology, he was also hinting on a similar future. Because the types of sensors you need on the wall are not the type of computing devices you need on your hands or on your desktop. So you can leverage this combination. Like if you think about forests, I think of organic materials as computational materials, and forests are like large computers that expand with sensors and actuators throughout miles and miles, and they play a role in the organics of like our planet. Yeah. So why not have our own computers?
But another way to look at this, Danilo, is someone will say, Gregory, you're never going to be able to produce something this powerful as this smartphone and have it be self-powered. And I said, that may be true. But when I now can turn an entire wall into a harvesting surface, I can harvest more. We don't take advantage of surface area. And there's a lot of surface area in the world and a lot of opportunity to harvest from that surface area. And then maybe we don't self-sustain a device like this, but we can harvest a lot more energy around us from the table that I'm on. And that can be used to do the same kinds of things in a different, more distributed fashion than what I rely on this brick for.
An interesting side conversation happening in chat brings up vulnerability, right? So physical vulnerability is a huge thing in security, right? Like where are your vectors? And if your entire literal outside of your building can be hacked, that'd be an interesting problem.
Yeah, so the security piece of this. Yeah, I mean, so my computer architecture colleagues really push me to say this will only be interesting when this is programmable, right? Because that's what they consider a computer to be, something whose behavior you can change. But as this comment here from Owen points out, as soon as you make it that changeable, then you open it up, who's allowed to change and who's not. So there is an argument for single purpose capabilities that cannot be changed. But there will always be this push, I think. You've seen it again and again. As soon as we have really good single purpose things, someone says, well, that single purpose thing will be even better if it could do this yet another thing. Let's update it. Let's add apps to it. So I don't have a good answer for you how you handle the security piece of it and what's different about security in a programmable computational material from any other programmable device.
I wonder if the analogy that really should be drawn is actually from building materials, right? You think about rebar. There's foundational properties that in which when you design with it, there are considerations, right? And those are structural, but they're also leads to design. In this case, I guess rather than thinking of something more like, oh, this computational materials, the endpoint is like a computer or a phone, let's say. Maybe it's more like each of these materials is a selection, like a rebar, like a concrete, and a type of concrete. Right? You have the super light concrete that has big balls in the middle of it that you need to build with that. There's techniques in which you use them, right? I wonder if that's really kind of the direction in which they're more foundational pieces.
Well, I mean, those are the two extremes we talked about. Can I think about computational materials as these highly disposable things and maybe limited functionality, but so cheap and responsibly manufactured and disposed of, or highly enduring materials that will add additional capability, but will be around for a long period of time and provide physical structural things as well as computational. That two very interesting and very different ways to think or to take this. Very good, stimulating discussion, folks. Thank you.
Yeah, as long as we've gone.
So I'm now supposed to meet with your
I
folks?
think they're all here anyways.
Oh, do we want to just stay here? Because we had the thing in gather time. We could just stay here and continue talking if you guys want.
Yeah, I mean, it's more inclusive in some ways because there's a whole other people around. So
sure,
up to everybody. I have no preference.
I'll need to get some introductions or let me know. I mean, I can see your names, but that doesn't tell me that much.
There's lots of people. For those who want to stay and keep chatting, feel free. For those in the class who felt trapped and can't leave.
Yeah, you can leave now. I'll close my eyes. I wasn't looking at any names, and you can just leave quietly.
I think we've stated. Not to play any favorites, but just to say who are my students. So of the people who have stayed so far, Tom's one of mine. Jessica, the two Jessicas are both my students. Owen's my undergraduate, is one of my master's students, and Varun, who is labeled UbiComp Lab, is in my lab. And then Chris, who is labeled as CR, hangs out with us sometimes. He is not technically part of our lab, but
it doesn't matter.
We like him.
Excellent. Yeah. Well, it's good to meet you folks. And I look forward to getting to know you even better over the coming years as you move through your educational experience with Edward and others. Anything you want to talk about? Or
Keep grilling him.
Yeah, it's so nice meeting you. I actually have another question. You talked about like the two sides, one of them being, can we produce something that is going to be durable in the next 50 years? But that seems like, how would you approach to predict, okay, can I extend this? Can I build up on this so that it will be useful in the next 10, 20, 50 years?
Well, so I think there's two things to that. One is, can you produce something that, given a static, a from its beginning functionality that doesn't change, that will simply just last for decades? So, it won't change its capability, but it won't stop working and it won't be damaged. That's one way to think about things.
Okay.
But then the problem with that is you're fixed with its capability. But of course, I'm fixed with the capability of a brick from the moment I put it in my house.
Well, you can patch it though, right?
Yeah, you can destroy it and use it to build something else, maybe.
Well, okay, but it's ceased to function as a brick at that point. So I can take my computational materials and dispose of them and reconstitute them as something else. Sure. But the first thing I think is, can I build something that will endure and keep its capability over time? And that's where I think things like these thin, multi-layer, simply manufactured materials actually have a lot of promise. That Saturn material, or that idea behind Saturn, lots of different materials you can use. You can do it in such a way that it could be placed on the floor and you can be continuously walked over and not degraded, particularly if you put it underneath, a carpet, for example, and its capability will not degrade over time, or at least I think that's quite possible. The more challenging thing is to allow something to be, upgradable in place, to basically wirelessly flash something so that I can change its capabilities. And that's where people want to go. And that's what I mean by this, that vision of, things will become more and more functional because you'll make these kinds of materials that can be, programmable and upgradable. I don't have a solution for that, but I think it's certainly an interesting direction to go.
Okay. So we kind of have to make sure that something's gonna be, that we have the capability to keep something useful when we design it to last for a long period of time.
Mm-hmm.
Okay, so yeah.
Right. So what would be a use for something that would persist over time? Well, let's think about a physical, a volume, a space, like a room, right? It's probably always going to be useful for a room to know about its contents, what objects are where, right? And if you can provide that capability, I don't think that capability would become obsolete. Now, you might want to do better things, but I don't know that you would no longer need knowledge of what objects are where in that room or how many people are in that room, for example. I mean, take the example of this, my desk here, this surface here. If I had objects that I could place on that surface and the contact between those two objects would communicate that one is on top of the other, like the table would know that this piece of paper with a unique identifier is on top of it. And that could be transmitted, something is placed on top of the first piece of paper. You can transitively know that objects are on top of each other because they're physically touching. I could understand what are all the things that are on this surface.
Yeah.
And because this surface is attached to something like the ground, I could communicate that information to the floor, to the wall, to the house. And I could ultimately know where every object is located, simply because every object touches some other object.
Yes, that makes sense. But how do we make sure, it seems obvious right now that this is useful information, but kind of thinking about what happens in 50 years, how do we make sure that this is still useful information. This is like kind of philosophical. Maybe there's like no answer to it.
I don't imagine in 50 years we will no longer have physical objects, right? And I think it may still be useful to know where those physical objects are. Yeah, I might want to do more things like move particular objects, but or maybe communicate across more than just the object I'm touching. But I can see some value in things that are in contact with each other, exchanging information about their identity so that it can be communicated up and down a chain. Right? I set my glasses down on the table. Where are my glasses? Oh, well, they're on the floor says to the table that, oh, it's sitting right there on top of the table. Right?
Yeah, thanks so much for answering.
Why don't you guys tell me a little bit about what you're doing? Or you can ask me questions, that's fine, but I want to know about what you're thinking, what things you guys do too.
No one wants to start.
So we'll start with UDComp.
I'll head out. I gotta go, but
all right.
Take care of them.
Okay, see you, Edward. And I've got someone else coming in a half an hour, I think.
So I told them to just pop on here. I figured,
great.
That'd be easier. And hopefully when I hit end, it doesn't kill everybody off.
Well, if it does, we'll go to Gather Town.
I think.
Oh, you're
All
host.
right.
Yeah. Okay. Take care.